Hey all listeners, this is Prajesh Chaudhary, your content guru. In this video, I am presenting to you a very good question of Irodov, that is from hydrodynamics. It's a 1.321 question number. So let me read the question. So this is the diagram for the question. The question states a side wall of a wide open. This is a wide open tank is provided with a narrowing tube. This is a tapering tube or narrowing tube through which water flows out. The cross-sectional area of the tube decreases from S is equal to 3.0 centimeter square to S equal to 1.0 centimeter square. The water level in the tank is H higher than that in the tube. So what we have to find? We have to find the force exerted, the horizontal component of the force by the water flow on this tapering tube. That's what we have to find out. So here is the diagram of the given question. This is a tank, wide tank. This is an open tank. This is a tapering part. The areas given are capital S and small s. So I have chosen the part where the area was capital S. I have written as S2. The part of the tapering tube where the area was small s, I have written S1. Corresponding radii are SR1 and R2. Alright. So as the fluid flows like that, because of the pressure is always perpendicular to surface. So at all these points of the tapering part, the pressure force would be like that, like that, like that. So the component of the pressure force normal to the flow will cancel and along the flow will add up. So there will be a net force in the horizontal direction. One more thing, that in the question it is not given anything, and it is not said anything about the atmospheric pressure, so we will neglect it. In fact, the answer given the Irodov will come only if you neglect the discard the atmospheric pressure. So we'll start with applying the Bernoulli theorem at this point and this point. Here the pressure is P atm, here is pressure is P atm. There are three types of energy: pressure energy, kinetic energy and potential energy. So at the 2 points, pressure energy is the same, so only energy that are interchanging between them are kinetic energy and potential energy. So it's just like a ball moving in air. So the loss in potential energy per unit mass per unit volume would be rho gh, and that would equate to the gain in kinetic energy. So from the Torricelli theorem directly, the velocity of a flux here would be square root of 2gh1. Or else you can apply the Bernoulli theorem. So here this velocity is v1, that is square root of 2gh. So v1 square is 2gh. And now let's take a general section somewhere here. So this is a general section, and at this general section the radius of the section is say small r, and the velocity here is v. So pressure here at the outside was PO, that will equate to 0, and the pressure here is say P. And before we apply the Bernoulli theorem, first let me apply the continuity equation though for this part and this part. So continuity equation says that if the fluid is incompressible, so volume flux mean the volume flux towards section are the same, mean the amount of volume flowing per unit time at all section is same. So volume flow rate here would be the area into velocity, and that is also here. So equate area into velocity, product of area into velocity at this section and this section. So here that is the area of section is a pi r square, velocity is v. Here area of section is pi r1 square, velocity is v1. So equate these things, we'll get v is equal to from here r1 square by capital R square into v1. That is one equation. And pressure here we assume to be P. Pressure here is PO, that will equate to 0. So apply Bernoulli theorem from this point to this point. So we'll write P plus half rho v square is equal to P naught plus half rho v1 square. So P naught is 0. So P here would be rho by 2 v1 square minus v square. So write everything in terms of the known thing. So take v1 square outside. So we'll get half rho v1 square 1 minus v square by v1 square. And from here put the v by v1 as r1 square by r square. So that would be r power 4 divided by r1 power 4. Reverse, r1 power 4 divided by r power 4. So at this general section the pressure would be, and one more thing, this v1 square will write 2gh. So that thing will become rho gh and 1 minus r1 power 4 by r power 4. Okay. And now let's once again let's have this point here, and I'm taking this section here, just cut these two sections. So this section is a small disc type of element. The radius is r, and if I just give you another view, so that would appear like that. And this is the slant length. This length is dl, this is r. So if I cut it and just make it a rectangular strip, so its area would be 2 pi r into dl. The area would be 2 pi r into dl, and before area, if radius here is r, and radius at this radius is gradually increasing if I'm going from here to here. So radius here is r and radius here is r plus dr here. So increase in the radius from here to here and going at dl length is dr. Suppose this angle is theta. So from here you can see that this dl is equal to, basically sine theta is equal to dr by dl. So dl is equal to dr by sine theta. So dl is equal to dr cosec theta. And area, I told you, this 2 pi r into dl put in terms of this dr. So area is 2 pi r cosec theta into d theta. Okay. So what we got? We got the pressure at this point was this. Area of this element, not this area, that the surface area. The surface area of this element is 2 pi r cosec theta d theta. And because of the fluid, the pressure force would be perpendicular to surface like this, like this, like this. So on this element, this enlarged part is the pressure force on the area dA would be PDA here, that is a dF. So for this PDA, there would be one component along this direction, one component along this direction. These components will add up for all the surface points. So net force due to pressure would be the vector sum of this PDA sine theta. So that will be in the horizontal direction. So net force on this tapering part would be along the horizontal direction, and that would be for this much part, that would be PDA sine theta. For the whole part, that will be integration of that thing. So put the value of P and put the value of dA, so that will get dfx, and then integrating that thing will get the total force. So dfx is equal to this P is equal to rho gh, and rho gh into, I've just multiplied it, just simplified it, just you multiply these two things. So rho gh and this r and this multiply this, so r minus r1 power 4 by r cube, and 2 pi I have written here, and cosec theta into sine theta, that would be 1. This is df of x. And integrate it. The variable is my small r. So the variable, so if I go from here to here, here small r is r1 and here small r is r2. So I'll integrate from r1 to r2, and this is a simple integration. This part you can do your own integration. So I'll directly write the integration. So after integrating thing and putting the limit, I will get this thing. And then I want to write in terms of area. Pi r2 square was s2 and pi r1 square is s1. Just rearrange the thing, and that much mathematics you can safely do. So on doing all those mathematics, you will get the fx part, the horizontal part of the fluid force, that would be rho gh s1 minus s2 whole square by s2. Alright, and there is another method to this question also. For that thing, this is the fluid part between the tapering tube, and we will draw the FVD of that thing. So this is in contact with the tube. So on this part the pressure is P1, the pressure here is P2, and this is a dynamic thing. Some fluid is being entered here and some fluid is leaving. They're not entering and leaving at the same velocity. Here the velocity is less and here the velocity is more. Equal mass is entering here per unit time, equal mass is leaving here per unit time, but not with the equal velocity. So there is a net change in momentum of entering and leaving part. So on this part, on the liquid is my system, so because of the surface the force would be like that. So for these two part, if the force on the tube by the liquid was along this direction, so force on liquid by the tube would be along this direction, and because the pressure force would be there. So velocity part that we have written earlier, so pressure is P2, pressure is P1. Because of P2 pressure here would be P2S2, and because of P1 pressure here is P1S1, and because of the tube there will be force here F. So that is what the FBD will look like. So for this part I will apply F net is equal to dP by dt, or you can also use the variable mass equation, F net plus F thrust is equal to m into A. The center mass has a zero acceleration, so for that thing you will apply F thrust, and here I am directly applying F net is equal to dP by dt. So, and before that thing, this V we had got R1 square by R square V1, and R1 square by R square would be the S1 by S. The area here is a small s. And V2 was this. V2 was basically V was this. So if I put here R is equal to R2, that velocity will be of V2. So V2 will be R1 square by R2 square. R1 square by R2 square would be basically S1 by S2. So this is S1 by S2 V1, alright. And same thing for the pressure. P is equal to rho GH, this is the pressure here. 1 minus R1 square by R power 4, R1 power 4 by R power 4. So using this expression, if I want to write pressure here, I have to just write in place of small r, that is R2. So P2 is equal to rho GH minus 1 minus R1 power 4 by R2 power 4, and this is S1 square by S2 square. So that is this thing. So now write the F net is equal to dP by dt. So F net is equal to P2S2 minus F minus P1S1, and dP by dt is the net momentum, net rate of change of momentum that is crossing the surface. So here this mass is crossing and this is entering, so the net momentum that is leaving the system, that is a dm by dt v1 minus dm by dt v2, that has entered, the leaving part is this. And dm by dt is the mass flux. So mass flux is the rho into A into V. Rho density, A area, V velocity. So dm by dt, here this P1 was 0, so this part I have equate to 0. So here dm by dt, just simplify that thing, you will get F is equal to P2S2 minus dm by dt V1 minus V2, and dm by dt either I can write rho 1 S1 V1 or rho 2 S2 V2. So I have written here rho 1 S1 V1, and just do some rearrangement using all those things, you will again get the same expression. Almost the same time would be take, so you can choose either method.